In this video, we're going to talk about polynomial functions. So first, let's start by defining a polynomial function. Okay, and there's a few things that go along with that. Okay, so we're going to define degree, leading term, and constant term. So a polynomial function in one variable is a function of the form, so we call it f of x, and it's going to have a constant a(n) times x to the power n plus a constant a(n) minus 1 times x to the power n minus 1, and so on until we have a1 times x and a0. So here a(n), a(n) minus 1, a(n) minus 2, etc. Okay, are constants. And we normally call them coefficients. Okay, n is a non-negative integer. And x is the variable. Okay, so that's a polynomial function. Okay, now if a(n) is not 0, okay, so the first coefficient is not 0, then it is the leading coefficient. Okay, and the term a(n) x to the n is the leading term. Okay, and n is what we call the degree. So it's the highest power of x that appears. Okay, now the a0, no matter what it is, so even if it's 0, is the constant term. Because this is the term with no x's. Okay, so it doesn't have any x's with it, so that's what we call the constant term. Okay, so those are some terminology. So let's look at an example. So here we have 7 x to the 5 minus x to the 3 plus 2/3 x squared plus root 2. So this is a polynomial function, while g of x is 3x to the minus 1 minus x to the minus 1 is not, and it's not because of this term. Okay, so polynomials don't have negative exponents. Okay, so we don't want a negative exponent. Okay, now talking about f, the degree of f, so you want to look at the leading term, so the biggest power of x, and take its exponent. So the degree of f is 5. The leading term is 7x to the 5. And the constant term is the one with no x's, so it's the root 2. Okay, now a polynomial is in standard form if its terms are listed. I'm going to change that to with powers of x in decreasing order. Okay, so they start with the biggest power of x and they work their way down. The graph of a polynomial is smooth, so what that means is it has no sharp turns or corners. Okay, so it's nice and smooth to draw. And they're continuous, so that means that they have no gaps, holes, asymptotes. Maybe I should write vertical asymptotes to be clear. Okay, etc. So what you can think for continuity is, so continuous means you can draw the graph without lifting your pen. Or pencil, depending on what you're using. So a power function is a function that just has one term. Okay, so it would look like f of x is some constant times x to some power. Okay, where again, so here a is not 0 because we don't want just 0. And n is a non-negative integer. Okay, so that's what we call a power function when it has only one term. Okay, now when we graph these things, they have specific shapes. So depending on if your power is even or odd. Okay, so if your power, so this, no matter, this is the same if there, even if there's an a. So this is using a equals 1. But it doesn't matter because remember a would just vertically stretch it. So the shape would be basically the same. So here they've drawn you the first 3 power functions. So for n even, we have the x squared graph that we're used to. Okay, but then we also have the x to the 4th graph, which looks very similar, but it just opens a bit more slowly at the beginning and then a bit faster after you pass the point 1, 1 and negative 1, 1. Okay, and same with x to the 6th. So it opens a bit slower when your when your x values are less than 1. And then as soon as they're bigger than 1, it goes faster. Okay, so they just keep doing that. And it's the same with the odd functions, except they follow the x cubed shape. Okay, so there's the x cubed. So all of these meet at 0, at x equals negative 1, and at x equals positive 1. So they're a bit slower until you reach negative 1, and then or positive 1 or negative, and then they grow faster. Okay, so these basic shapes we should know. So all of them look like that. Okay, and then when you start adding more terms, then they change a bit. Okay, now I'm going to skip this one because it's something that we've done. But you have the graph of x to the 5. Okay, it's the dashed line. Okay, so that's the one you want to use, and you just want to do a couple transformations to it. So let's start talking about roots and zeros. So if f is a function, and r is a real number, with or for which, so f of r is equal to 0. Okay, then r is called a real 0, okay, or real root of f of x. Okay, so these mean the same thing. Now notice that when you plug in r, you get the y value of 0. So this actually means x equals r, or maybe I should write it as a point. Okay, so the point r0 is an x-intercept. Okay, so that's all this is saying. We're just giving them a different name. Okay, so if you plug in r and you get 0 for the y value, then we call that r a 0 or a root of the function. So I guess here, these are all equivalent, so this is saying the same thing. So the first two are the ones I just mentioned. So you have a real root of f of x, or 0. That's the same as saying this point is an x-intercept. It's also the same as saying that x minus r is a factor of f of x. So you should be able to factor it and get x minus r out. Now I'm just going to add this fourth one, which is the definition for a real root. Okay, so r is a solution to the equation f of x equals to 0. Okay, so that's the same idea. So if they tell us what the zeros are, we can find an equation for a polynomial that satisfies that. Okay, so if I get the 0, so I have 0, so first one is minus 2. Okay, so that tells me that x minus negative 2, or x plus 2, is a factor of f of x. Okay, by number 3. Okay, now 2 being a 0 tells me that x minus 2 is a factor. And 3 being a 0, or a root, means that x minus 3 is also a factor. Okay, and now that means that f of x has to be these three things multiplied together. Okay, now this is going to give us a degree 3. So it wanted degree 3 here. This is going to be degree 3. So if you multiplied it out, you would get degree 3. The way that I know that is I'm going to have to expand everything, right? And I have 1x here, 1x here, and 1x here. So the biggest thing I could have is this one times this one times this one. So that's going to be degree 3. So this would be a polynomial that is degree 3 and that has these zeros. Because if this is 0, then negative 2 makes it 0, positive 2 makes it 0, positive 3 makes it 0. Okay, now is this unique? Okay, so the answer here is no. Okay, so it's not unique. Because I could, it is fairly unique, but I could, let's call it g of x. I could just multiply by a number. Okay, so I could have like 2 times x plus 2, x minus 2, x minus 3. Or I could have like a negative. Maybe I have negative 5. Okay, but I still need all of these factors in order to have it be 0 when the y value is 0. I can't add to it because then the factors don't work, but I can multiply by a number. Okay, so we could multiply by a number and get another polynomial that has the same properties. Okay, so multiplicity. So if x minus r appears more than once as a factor, then we say r is a repeated root. Okay, or 0. So if x minus r to the power m is a factor, but x minus r to the power m minus 1 is not, so basically that just means that this is the biggest. Okay, so that's the most number of x minus r's that you can factor out. Then we say r is a root, or 0, okay, with multiplicity m. Okay, so that's because it occurs m times. Okay, so let's do an example here. So when it's factored like this, you don't have to really worry about this property. It's just to the power that it occurs. Okay, so what are the factors? Okay, so I have definitely x minus 2 and x plus 5, but I also have this 0, or this x, sorry. So any factors that have x's in them, so that are multiplied, so I could write it as x minus 0 if you want. Okay, x minus 2 and x plus 5, which is like x minus negative 5. Okay, so that means that 0 from the first one is a root. Okay, so from that, 0 is a root, and it has multiplicity 1 because the power here is only 1 on that one. Okay, now this next one comes from here, so what would make that 0 would be 2. Okay, so 2 is a root. Now 2 has multiplicity 3 because x minus 2 occurs 3 times. Okay, and then we also have negative 5 as a root, and it's going to have multiplicity 4 because it occurs 4 times. Okay, so that one comes from here. Okay, and then what you're doing is you look at their powers to find the multiplicity. Okay, so if r is a root of the polynomial, then, like we mentioned, r0 is an x-intercept on the graph. So there's two possibilities that could happen when you meet an x-intercept. So you either cross the x-intercept or you just bounce off of it. Okay, and this happens when your multiplicity is odd versus when it's even. Okay, so maybe I'll just draw a little picture here. So for an odd multiplicity, maybe I'll just draw one picture. Let's do it down here. Okay, so if my function looks like that, okay, so here I have an x-intercept, and here I have an x-intercept. This one is going to have an odd multiplicity because it crossed the x-axis. Okay, this one is going to have even multiplicity because it just touched but didn't cross. Okay, so that's the difference. So in this example above, okay, here, this one will cross at x equals 0. This one is also going to cross at x equals 2, but this one is going to just touch at x equals negative 5. So it's not going to cross. Okay, because of the multiplicity is even. Okay, so let's do an example. Well, actually, no, I'm going to skip this example because I just talked about it with that example. So I'm going to skip this one. So you want to find their roots, their multiplicities, and then determine if the graph crosses or touches. So let's talk about end behavior of our polynomials. So the end behavior is the shape as x gets really big or really small. So as x approaches positive infinity or negative infinity. So for polynomials, the end behavior is determined by the leading term. Okay, so for example, if I had this polynomial here, okay, 2x cubed minus 18x squared plus 1, the end behavior is going to be the same as for the leading term, y equals 2x cubed. Okay, now we know what the graph of 2x cubed looks like. Okay, it's the x cubed graph, but it's stretched a little bit. Okay, but it has the same basic shape, so I don't actually care much for the picture. But what the end behavior looks like, so what we would show for end behavior is we would say, okay, as x gets really big, it leaves that way. okay, and it leaves this way. So that's enough information to talk about the end behavior of f of x. Okay, it's the same as here. Okay, so what way are the arrows pointing? Okay, now there's only 4 different types of end behavior. So they depend on the degree and then whether or not the leading coefficient is positive. Okay, so let me just draw a little axes in here. Okay, for each one. So if we're even, you want to think, so let's start with even degree. So if we're even, you want to think about, you can imagine x squared. Okay, x squared is an even degree that we're comfortable with. Okay, now we know that x squared normally looks like this. And this is when a is bigger than 0, right? Because it's for a equals 1. So that means that the end behavior looks like that. Okay, now if it's negative, that's going to flip it over if the leading term is negative, that's going to flip it over the x-axis, and it's going to go like that. Okay, now similarly for odd, you could think about y equals x or y equals x cubed. So we know normally they do this, and when the leading coefficient is negative, you flip it over the x-axis, so it's going to do that. Okay, and those are the only 4 types of end behavior. So they just depend on the degree and whether or not the leading coefficient is positive or negative. So it's easy to determine these things when the polynomial is given in standard form. But if it's given in factored form, it's a bit harder. So it's easier to find the zeros in that case, but harder to find the end behavior. So if you have two polynomials that are multiplied together, okay, if you want to find the leading term, all you have to do is take the leading term of the first one and multiply by the leading term of the second one. Okay, so for example, here I'm going to take the leading term of the first one and multiply with the leading term of the second one. So the leading term of the product is going to be 2x cubed times 3x, which is going to be 6x to the 4. So now I can tell that the degree is 4 and the leading coefficient is 6. Okay, now if I have a polynomial to a power of n, and I want the leading term of that, then I'm going to take the leading term of the inside and raise it to the power n. Okay, so again, here we have our polynomial. So we take the leading term, which is the biggest power of x. So this is going to be 2x cubed all to the power 4. Okay, so that's 2 to the power 4 times x cubed to the power 4. So that's going to be 16. And then I multiply these powers to the 12. So I'm going to have degree 12, leading coefficient 16. Okay, so if f of x is factored, we find its leading term by looking at the leading terms of each factor. Okay, so that's what we want to do. Okay, now there's a couple of examples here. I'm going to do number 5. Okay, so here I have a polynomial. It is a product of a bunch of other polynomials, one of which has a power. Okay, so I'm going to take the leading power, the leading term in each. Okay, so that's going to be the 2x from this one. It's going to be the negative 3x squared from that one, and the x from this one. Okay, so that means the leading term, the leading term of g of x is, so it's going to be 2x times negative 3x squared cubed times x. Okay, so that is going to be 2x times negative 3 cubed x squared cubed, okay, times x. So that's 2x times negative 3 cubed is negative 27. X squared cubed, that's going to be x to the 6, okay, times x. So now I have 2 times negative 27 is negative 54. And then I have 8 x's. Okay, so that means that it has degree equal to 8. Okay, so even degree. And leading coefficient of negative 54, which is obviously less than 0. Okay, so the end behavior so the even one with a negative coefficient is going to go down and down, like that. Okay, so that's how we determine that. Okay, now I'm going to leave this one for you to do. And there's 2 more examples on the last page for you to try as well. So I'm going to leave those for you. So that's sort of the introduction to polynomial functions. So finding all their important behaviors. Okay, so what they do around the x-axis and what they do when x is large. Okay, so that's what we've talked about here.